Hello, people. What's going on, everybody? I guess it's just the four of us today. Oh, and five, six, seven. Oh, we're I'm so happy. I'm so happy. This becomes so popular already. Let me
Yeah.
welcome back to discrete math class. How was everybody's second day of fall 2020? Silence. Okay. That might sum up this semester. So check this out. Figured out how to do that so you can see my face and see the whiteboard at the same time. And I have a desk, kind of. It's all coming together. We're
Is
doing.
this the same desk from yesterday?
Well, this is the same desk from yesterday. Now it's actually on legs.
Ah, I see.
Yeah. So, I mean, it's kind of like a Theseus is ship situation. Like, is it the same desk or has it become something totally different given its new context? But anyway, let's see here. Let's line all that up. Nice. This is upside down, isn't it? Let's try. Yep, we can fix that. Okay, this is there we go. All right, well, welcome back everybody to discrete. Wait, what's happening now? Why is it on? And then. There we go. Okay. What's up, everybody? Welcome back to Discrete Math. This is the second day of class. Last class was a very pie in the sky, I think, is a metaphor. What's that a metaphor for? Pie in the sky, like introduction to class, very loose philosophical discussion about what we're going to do in this class. And remember, we said in this class we're going to do is it's all about arguing that a statement is actually true. And so write that down right now. And you can't see that. There we go. Is about arguing a statement is true. And we talked about what it means to be true last time. Last time, being true meant that you could connect it logically from another true statement. So at some point, you have to assume something's true. And then after that, everything else that's true is just connected to those assumed true things. But anyway, there's two big old words here that might not be obvious what they mean. Who wants to play guess the not obvious words? Well, okay, let's go through it. Process of elimination. Class, that's you guys. Is, I mean, Bill Clinton had trouble with what is means, but I think we all know what is means. It means to be, the conjugation of to be. About, actually, I don't know how to describe what about means, but the words that I care about here are arguing and statement. Right, this class about arguing a statement is true, but what's a statement and what exactly do we mean when we say to argue? So, let's just do a definition here real quick. The definition, a statement is any sentence that is either true or false. Those are two options. And I think that makes a lot of sense, right? Because they're trying to argue a statement is true. Well, a statement must be something that can even be true, right? It must seem weird. Like, it's like, well, what can't be true? What can't be false? Let's go through it. So first is doing examples of what a statement is. These will be nice and easy. So for example, we have Justin Fuente has 3 arms. Is that a statement? Nice thumbs up. Exactly. Yeah, it is a statement, right? It's false, but it is a statement. So what I'm going to do is I'm going to write this like kind of triple equal sign with false. I should do F for false. And so the triple equal sign, that means logically equivalent to, because every statement, remember, is either true or false. So every statement in a certain sense equals true or equals false, like Boolean algebra and computer science, right? So Justin Fuente has 3 arms, the statement that is false. So we do 3, so we say logically equivalent to false is the way to put it. Anyway, yeah. And I had to lie about Justin Fuente because any true things I say about him would not be very nice. But anyway, so that's a statement right there. Another statement would be red is a color. And red is a color, that is true. It's a true statement. We could also do that North Dakota is a province of China. Unless the maps have changed, that is a statement and it's false, right? And notice that all of these statements, they have, it's kind of like a regular, well, they're sentences, right? Just like your English teacher taught you to have a subject and an object, right? Like Justin Fuente is the subject of the statement, and what's happening to him? He has 3 arms, right? Red is a color. North Dakota is a province, right? So it doesn't matter if it's true or false to be a statement, it just has to be true or false. So is every sentence a statement is the question. Who thinks yes? Who thinks no? Who doesn't think anything at all? We got chat. Yes. We got yes and a no. So I'm sorry if I mispronounced your name. Is it Benet?
Yeah, that's correct.
Nice. So Benet, why do you think every sentence is a statement?
Because it needs to have some sort of like dependency clause within it, I guess.
Mm-hmm.
And that's either going to be true or false. This is a car. That's true.
Interesting. You're totally right about you're right that it's going to have a clause, right? But the question is, does it have to be true or false? Someone that said no, like Ronaldo or Toru. I'm sorry for mispronouncing any of those names. Why do you think no?
So I guess based on what we sort of talked about as of now, every statement is true or false. Well, then what happens if you sort of like pose the statement or a question as, is it going to rain today? It could be true or false if you don't have enough data, but to provide more observation or information, then that question turns into a statement.
That's interesting. So is it going to rain today? So you could argue though that, I'm not using this for argument, but you could argue that if you're going to say, is it going to rain today? Are you saying like in Blacksburg? You're going to say, is it going to rain today in Blacksburg? I mean, we don't know what's going to do now, but we know eventually we can go back and verify, was that true or was that false? So that does going to have a true or false. But what about this? What if we said, is it going to rain? What if we said, it is going to rain today, and we had no context as to it is going to rain today, like where, right? Or maybe a better version of this. Let me grab my little eraser thing. Let's be real, it's a washcloth. But anyway, what if we said something like, he plays ukulele. Is that true or false?
Could be either true or false if we don't have.
Depends on who he is, right?
Mhm.
So this is not a statement. Because it depends on who he is. So just saying this statement, he plays ukulele, is not really a statement. Same as saying like it's going to rain. If you don't specify where, you know what I mean, or like what time or something like that, then once again, it just depends on what you're talking about. So this is not a statement because it depends on who he is. Now notice, as soon as you define who he is, if you put Daniel Balvo plays ukulele, the answer is true right there. If you put Justin Fuente plays ukulele, maybe not. If you put Barack Obama plays ukulele, you know, it's going to be true or false depending on who you put in there. Now, another thing that might not be a statement is, for example, let's say pineapple on pizza tastes good. Now, this is an interesting one because this one right here, he plays ukulele. I totally see why Benet might be a little upset by that and go, well, that's a little unfair because he plays ukulele. It is a statement. This sentence is a statement just depending on who he is. And in real life, you would never say he without it being clear from context who he is. But this one, pineapple on pizza, we kind of do have a subject, right? Pineapple on pizza, and we're saying it tastes good. But what's wrong with that?
It's very subjective.
Very
There's no
subjective.
like answer.
It really there's no real answer. It really depends on. This is not a statement because it depends on who you ask. Another way to put it is, like you said, it's subjective. So it's not really true or false. It's a perfectly valid English sentence, but it's not true or false. Now, there is some question about does everything have to be true or false? And there's actually some weird logic out there where people don't assume that things have to be either true or false. But for this class, we're going to keep it simple and say a statement is something that is true or false. And this is actually called in philosophy the exclusion. Oh, what's it called? It's called the, I just looked it up. It's called like the exclusion of the middle or something like that. Basically saying there's no middle ground. It's either true or it's false. That's just it. This is what statements are. So this is a version of statements. And so far we did a bunch of very English-based things, but there's no reason to. I mean, I don't really know any other language, but I do know some more mathy-based things. So let's say, for example, I said 17 is odd. Is that a statement?
Yeah.
Yes.
Right? Obviously, it has a truth value, meaning it's either true or false. And in this case, it is true, so it is a statement. But what if we said x squared plus 2 equals minus 2?
It's always false. Unless you're
True
taking
in
like
certain
imaginary
conditions.
numbers.
Yeah. So this one is going to be not a statement. because depends on X. Now you're right that this is never going to have a solution in the real numbers, but nowhere here did I specify that X is in the real numbers, right? It could be an imaginary number or something like that. The point is we have no subject here, right? We have an object, right? This is like saying,
Oh,
or I'm sorry, so we have a whatever, but it's like long excluded middle. Thank you very much. There we go. But yeah, I mean, it's like saying go to the store. Who went to the store? Like there's no subject to even talking about here, so there's no way to verify if it's true or false. So this is not a statement, depends on X. Let's see. Now I'm gonna test you guys. Test. But what if I say x cubed minus 17 equals 5 for x equals 1? Statement or not a statement?
Statement.
Statement. Totally, right? Because we know the subject x equals 1. And we're saying that if you plug it in this equation, we're going to get the same value on both sides, right? We're just going to say that 1 cubed minus 17 equals 5. Doesn't matter if it's true or false. We just know it's going to either be true or false. So this whole thing is a statement, and it's going to equal false. But it is a statement. How about The Rock is an actor, and how do you spell Oprah? O-P, is this O-P-R-A? Is there not an H in there? I feel like I'm spelling it wrong. Go with it.
there's an H at the end.
Oh, right there. Nice. And Oprah is Pope. That a statement?
It
Yeah.
is a statement.
Yes. Good job. Good job. It is a statement, and it's false, right? Because even though The Rock is an actor, Oprah's not Pope. So it's not true that The Rock is an actor and Oprah's Pope. So one way that we can kind of write this is if we want, this is a statement in and of itself, right? And this is also a statement in and of itself. And so we could have done something like, okay, call this, say that's equivalent to P. Just name it something. This is just like, you know, in whole like gravity, where like F equals G M1 M2 over R squared, like by Newton's equations. This big G is a number. It's an actual number, right? But they just write big G for convenience because it's really long, it's a lot of decimals. Same thing here. Just for convenience, let's name this statement. Oh, that's unfortunate. Let's name this statement that The Rock is an actor. Name that P. And then let's name this Q. And so in a certain sense, this right here, this whole statement, or not in a certain sense, it just is. This whole statement is equivalent to P and Q. Because in order for this statement to be true, right here, both P has to be true and Q has to be true. We'll talk about that more in a second. Anyway, what if I say 37 plus y for y equals 9? Statement or not?
Not a statement.
That wasn't an option. The options were statement or not. Yeah, I got you.
Nah.
Thank you very much. Yes. So, yes, this is not a statement because this time, like, because even though we have a subject, we're not saying anything about it. Right? There's no action happening to it. Right? I mean, we're adding 37 to it, but we're not saying it does anything. Everything else says it doesn't. The Rock is an actor. Right? There's like a verb there. It says it's doing something. 37 plus y. What about it? Right? I mean, like, there is no like. I want to be clear here. This is not like, okay, these are English examples to help us explain math. No, they're all the same. This is all just logic. They're like this right here, x cubed minus 17 equals 5 for x equals 1. That is an English sentence. We just replaced some of the words with notation. Instead of writing an equal sign, we put two little equals. Or so instead of writing equals out, we put a little equal sign. Instead of writing minus, put a little minus sign, stuff like that. And by the way, they did not used to do that in math. All the way up until like the equal sign and the plus sign, the minus sign, and all that wasn't invented until like the 1500s. Before that, when people wrote out math, they would literally write out like X, PLUS, X. But like it was bad. It was very bad. But people just really complicated math with that really bad notation. The point is, yes, this is just logic right here. Like math is a part of it. We can use it on math, but we don't have to. Anyway, though, any questions about that? Oh, here we go. Let's see. Is it safe to say that it is not a statement if both booleans have a possibility of being correct? If y'all are taking digital notes here, the equals. Oh, good call. If both booleans have a possibility of being correct. Benet, can you clarify that question for me? So, are you saying
if the statement has a possibility of both being correct or incorrect depending on the context of the statement, does that mean it's not a statement? Like, it is going to rain today, where? That means both of them have a possibility of being correct, but it depends on where.
Oh. I see what you're saying. So, for example, like, what if you were to have a statement where it couldn't rain anywhere, kind of thing? Well, so this is where English gets a little messy because we don't always say what we mean. There's a lot of things that are assumed. In math, we're not going to have any of that problem. We're going to write down literally everything we possibly mean. Nothing's going to be assumed. But in a world where you're talking to a robot, right? You're talking to a robot that could speak English but had no sense of assumptions or like body language and what you actually mean when you say things. If you just told a robot it is going to rain today, his question would be where? Or if you said like an asteroid's not going to destroy you today, the question would once again be where? Like an asteroid's probably not going to hit Earth today, but what about somewhere else in space? Like you see what I'm saying? Like if you're talking to a robot, the robot would need to know everything you're talking about, right? Like it is going to rain today. Well, what is the it? I guess where is it happening? Things like that. But I think that problem that's kind of just a nitpicky thing with English, I guess. For with math, we're not going to run into that issue, so you don't have to worry about that. This all will eventually be applied to math. Hope that answers your question a little bit. All right, so next up, so those are statements. Next, we're going to talk about something we kind of already brought up, and that is compound statements. And here's where things really start cooking. The statements are cool on their own. And remember, statements are anything that have true or false values. But like we saw with the Rock and Oprah example, you can create new statements from other statements. So a compound statement is a new statement created from other statements. And I'll say usually using the not and or they're going to be called operators, but you really know what you know what that means right now. But anyway, yeah, using not and or operators, and their symbols are going to be not and or. So that's the little tilde thing, and is I guess like a right side up caret and upside down caret. So I guess the caret would go that way in the ground. You know what I mean? Whatever this is. So, yeah. So this is the definition of a compound statement. This is going to make a lot more sense if we actually do an example. So, for example, let's go ahead and let P, for the rest of this little whiteboard we're going to do, let P be logically equivalent to the statement Justin Fuente has 3 arms. That's just what P is. It's like the G for the Newton's thing. We're just calling it that. Then we can make a new statement, not P, which equals Justin Fuente does not have 3 arms. So the not thing, this is just the negation. It just means the opposite of P. Now question, does every statement have an opposite?
No.
Yes.
No, not necessarily.
Can you think of an example of one without an opposite?
Like The Rock is an actor.
Mm-hmm.
Oh, The Rock is not an actor, I guess. I don't know.
Yeah, because this doesn't matter if it's true or false, right? It just doesn't have an opposite statement. So the answer is, I'm not going to think too long because there is no example, because every statement does have an opposite. And I'll write that over here.
Right, but so the only condition is that it has to be a statement regardless.
Exactly. Like the thing that you're putting before the not symbol has to be a statement. But as long as that's true, it's gonna have an opposite.
Right, yeah. So yeah,
Yeah.
I mean, since P is always true or false, not is just false or true.
Exactly. That's a good point to put it. So if P were true, not P would be false. If P were false, like it is in this case, not P would be true. I think I should write that because we know this is false, and so this is true. So that's just what not P does. It just flips the truth value from true to false. But it is kind of interesting that every statement does have an opposite, and kind of what you do is you just put a not in front of the verb, and then that makes sense. But anyway, that's what not does. I think it's pretty simple. Now let's do and. So I don't need to keep writing an example. You guys know what we're doing. You know what's up. Let's let Q equal x squared minus 2 equals 7 for x equals 3, which is true, right? Because you plug 3 in, you get 9 minus 2, that equals 7. Ayo, there we go. So Q is true, finally. And then, we could do not Q. That just means x squared minus 2 does not equal 7 for x equals 3, which is a false statement. And you can just put parentheses around things just like, I'm just doing that like you would in math or computer science, just to group it. But yeah. So that's what not Q is. But now a little more interesting, I think we got that, is what does P and Q mean? Remember, that symbol means and. So that just means that Justin Fuente has 3 arms, and x squared minus 2 does not equal 7 for x equals 3. So this is just, you literally just put and between the two statements, right? And so this is true if both the first statement and the second statement are true. And so this equals this is logical equivalent to what? Justin Fuente has 3 arms. We said that's false. X squared minus 2 is not equal 7 for, or no, I'm sorry. Q had an equal sign here. It was the not Q at the not equal sign. But so Q is x squared minus 2 equals 7 for x equals 3. We said that was true. And so is this statement as a whole, P and Q, is that true or false?
False.
False, exactly. Because one of the things is false. It's not true that both P and Q are true. Q is true, but P is not true. So they're not both true. So this is false. As a whole, it's false. But now if we were to do P or Q like that, this would be, actually I'll do Q or P. This would be Justin Fuente has 3 arms, or x squared minus 2 equals 7 for x equals 3. So this is basically saying, remember, just when they ask the arms, that's still, I wrote P or Q. I wrote Q or P because I was going to flip it up, but anyway. So let's do P or Q. So just when they has 3 arms, or x squared minus 2 equals 7 for x equals 3. So just when they has 3 arms, that's a false statement. Or true. So the question is it true, like if you have an or, that just means one of them has to be true. P or Q means P is true or Q is true. One of them has to be. So is this whole statement P or Q true here?
True.
True, exactly. Every one of them is true. We're starting off simple, and I hope this seems almost so simple that we're wasting time. Because if the whole class seems like so simple we're wasting time, then the whole class is simple. But at the end, we actually did something. Because it's all going to build. It's all going to be awesome. So, these are compound statements. Any questions on these? Cool, nice. So I hope that means we're doing good. There's a little caveat talking about, or I guess one thing we should talk about a little bit is if P is a statement, if P and Q are statements, is P and Q, like, well, let's write it down. The question would be, if P and Q are statements, is P and Q always a statement? Like, could you think of some weird scenario where P and Q are statements? They're sentences that are either true or false, but this P and Q is not a statement. It's not true or false. I hope silence means you guys think the answer is yes. It's always going to be a statement, but you're afraid I'm trying to trick you. But no, you're right. You're right. In this scenario, you're totally right. Yeah. If P and Q are statements, then P and Q is always a statement, and same thing with P or Q. So these compound statements really do always make new statements, as long as the things you start with are statements. So compound statement is a new statement created from other statements, just like that. Yeah. So let's do just some more examples of this. So let's say R is a statement, and R just says France is in Europe. And then let's let T be a statement. And who's got a statement? Who's got a statement for me? Could be anything.
It's a sport.
What's a sport?
Basketball.
It's my favorite sport. Do you know what my favorite part is?
Winning.
When they
dribble
put it
up
into
and
the
down
net.
court.
Exactly.
So basketball is a sport. That's R and that's T. And you know what? Let's change this to make it a little more interesting. Let's make France is in Africa, which is not true. So this is going to equal false, and this is going to equal true. All right, I think we can all agree with that. France is not in Africa, but basketball is a sport. So real quick, let's just do a little practice. If I did not R or not T, what would that mean? So what that would mean is, that would mean France is not in Africa, or basketball is not a sport. Is that true? Yeah. This is true because France is not in Africa. So it is true that one of these things, excellent question. I was just going to talk about that. So in this case, I meant not R or not T. However, this is, actually, we'll get to that. We'll get to that at the end. But for now, this is what, so Ben, you really good question, what's the order of operations for compound statements? And because if I didn't put the parentheses here, it would be kind of hard to tell. We're going to get at the end. We're going to stay on this train of thought for now. Anyway, yeah. So this is true because France is not in Africa. So one of these things is true. But here's a question. Is there any way we could have done this quicker and more efficient? Like figured out this statement was true without having to write out what all this meant and then think about it.
You could find the values of each statement and then just evaluate.
Yeah. Find the values of each statement and then go from there, because we know, right, that if anything that if we know that if P and Q, or we know that if, let's use P and Q. Actually, let's talk about this. So we could have said here that R, that not R, right? Or let's start here. Let's make a table. So R we know is false, meaning not R is true. And then T we know, based up here, is true. So then not T is the opposite of that, which is false. And then the last question is just what is not T or not R or not T? Well, we know R is true and T is false, but for OR we just need one of them to be true. So it's true. See what I'm saying? Because France is in Africa literally is false. It's logically equivalent to false. In fact, France is in Africa is equivalent to Daniel Valvo lives in a mansion. Now this is weird because Daniel Valvo lives in a mansion and France is in Africa are two totally different statements, but they're logically equivalent because they're both false. That's kind of interesting, right? That's all it means. So France is in Africa. France is in Africa, as far as we're concerned in logic, France is in Africa is just a really fancy way to write false. Well, okay, I should say this. I don't own a mansion. I could squat in a mansion probably if I really wanted to, but I don't own one. Oh yeah, so France and Africa and Daniel Balbo lives in a mansion. They're both false. They're both really fancy ways to write false, right? And basketball as a sport is a really fancy way to write true. So at the end of the day, R just is false, not R is false, T is true. That's just what they are. There's no need for us to go back to the English meanings and actually think about it once we know their truth value. I think that's kind of interesting, right? What we've done here is we boiled every English sentence or any sentence, really any communication that has meaning, that's either true or false, so any statement, we just boil it down to true or false, and then we can play with it. So the next thing we can do is start talking about which things are always going to be logically equivalent, and this involves truth tables. So this right here is kind of a truth table, but not quite, not yet. So a truth table, so this is our compound statements. I think we've said all we can say about this, really. We're going to do more examples in quizzes and homeworks and stuff like that, but I think it makes sense. Any questions on compound statements before we move on? Not really moving on, moving deeper. The math submersible keeps going. There we go. So let's talk about truth tables. The next big point of discussion. So a truth table is just a way to write out all the possibilities for a statement, for a compound statement usually, based on all the possibilities for its individual parts. So by this, I mean, so the truth table for P and Q would look like this. So we have P, Q, P, and Q. So in the scenario where P is true and Q is true, P and Q will be true. In the scenario where P is true and Q is false, P and Q would be, well, false, right? Because if P and Q are true, then both of them have to be true. If P was false and Q was true, this would also be false for the exact same reason, because not both are true. And if P was false and Q was false, this is certainly false, because not even one of them is true. So this is the truth table for this. We're just mapping out all the possibilities and seeing what happens. So notice that P and Q here, it's only true in one instance. It's only true if P is true and Q is true, which is duh, that's the definition of this. So now let's look at the truth table for P or Q, which, and actually, I'll just add it to here. Actually, I'm not gonna do truth table, just to show you guys how truth tables work. So if we had, here we have P, here we have Q, here we have P or Q. Again, if P is true and Q is true, well, P or Q, one of them is definitely true, so you're true. If P is true and Q is false, then P or Q, well, that's true, right? Because one of them is true. It is true that P or Q is true, P is true. Same thing if we have P false, Q true. In this scenario, P or Q is totally true. Now, if we had P is false and Q is false, P or Q would be false, right? Because not even one of them is true. So notice here, the scenario in which you're true is any scenario where one of them, either P or Q, is true, which once again, obviously, right? Because that's but the P or Q, we define it to be that way. So these are examples of truth tables. And right here, it might not seem like we really added anything. However, you might even say that in a certain sense, the truth table is more elemental than the word and. In a certain sense, this is the definition of this operation. The truth table is. And then we just write it like that. But it happens to mean the same thing as the English word and means to our brains. But anyway, that's not the point. The point is to say you write truth tables for things. And you write truth tables for more complicated things. So any questions on this? I think it's making sense. So let's say we had, let's say we're in the truth table for not P and not Q. So here, well, what do we need to do that? So the thing we're trying to do is we're trying to write what happens to not P and not Q for any options for P and Q. So we have P and Q, we're gonna need that. We're also gonna need to know what not P is at some point. We're gonna need to know what not Q is at some point. And we're gonna need to know what not P and not Q is. So, once again, our options are gonna be true, 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 false, false, true, false, false. And now we can just go down the list and just do it, right? So if P is true and Q is true, not P, false, right? Not Q, also false. Then not P and not Q, well, false and false, right? Not P and not Q means they're both true, but in this case, neither of them are true. So this is going to be false. Now if we look at here, true, so here we have P is true, so not P is false. Then not Q, well, Q is false, so not Q is true. And then we have not P and not Q. That's just asking, are both of these columns true? Right? That's the only way for not P and not Q to be true, if both these columns are true. But here we have one's false, so they're not both true. Making sense? So then we have false, true. We're going to have not P is going to be true, because the opposite of false. Not Q is going to be false, because the opposite of true. And then once again, both these columns are not true. It's not like not P and not Q, they're not both true. So this has to be false. There's a false in there. But then if we look at, let's say, sorry. So here we have not P is going to be, so here in the case where P is false and Q is false, not P is true, not Q is the opposite of false, which is true. Both columns are true. Not P and not Q are true, so we're true. So the point is, any complicated logical statement, you could write down the truth table for. Now, let's talk about something interesting. I'm going to keep the results of this just so we have it. So I said not P and not Q. That was false except for when, oh, whoops, erased too much. So we had true, false, true, false. So we said that not P and not Q, that's going to be false in every scenario except for when both P and Q are false. Hope that makes sense. Now let's look at truth table for P Sorry. For, that just sound weird. Not P or Q. So here we're going to do P or Q first and then negate that. Put the not operator on that. So take the opposite of that. So for that, we're going to need to know. Going to need to know P. Going to need to know Q. We're going to need to know P or Q. And we're going to need to know not P or Q. Whoops, I needed that. Why did I write all the boxes? Oh, we're gonna have boxes this time. I don't know why. There's a grid now. So once again, our options are P is true, Q is true, P is true, Q is Q. That is gonna be true. Look at that. P is false, Q is true, P is false, Q is true. Those are always our options. And by the way, on your homework and stuff like that, please write it like this to make our grading easier. So we know what's going on. Just always write the first column is true, true, false, false. The next column is true, false, true, true, or true, false, true, false. Call my own hair. There we go. Anyway, so we're getting somewhere interesting, trust me. So P or Q is going to be really easy. P and Q are both true, so it's true. How about P or Q and P is true and Q is false? Well, here one of them's true, so P or Q is true. P is false, Q is true. Well, once again, Q is true, so P or Q is true. One of them's true. And then if P is both false and Q is false, then they're both false, not either of them are true. And so P or Q is false. Then the not P or Q, we just take the opposite of that. So when P or Q is true, the opposite's false. True, opposite's false. True, opposite's false. False, opposite's true. Has anyone noticed anything interesting?
Is it commutative? Is that the correct word?
What's interesting is that both not P and not Q and not P or Q give the same values in the truth table. With the same inputs for P and Q, you get the same outputs for both these things, right? Like if P is false and Q is true, then this gives you false, this also gives you false. And that works for all of them. So what we've just discovered is the first logical identity we're going to have in this class. So you know how like there's algebraic identities, like for example, a squared minus b squared always equals a minus b times a plus b for a and b real numbers. There's actually essentially imaginary numbers. Let's just be simple. Right? That's an identity. It doesn't matter what a and b are. This is always going to be true. Same thing here. Not P and not Q is always going to equal not P or Q for all P and Q statements. And that's kind of interesting. And I think if you really think about it, this is going to make sense. Because if you have not P or Q, so if we're saying P or Q is not true, that means that both of them have to be false, right? Because if P or Q is true, then if P is true or Q is true, then P or Q is true. So if you want P or Q to not be true, you're gonna want both of them to be false, meaning you want not P and not Q. If that kind of makes any sense, you think about it that way. But anyway, you can just look at the truth tables and you totally see what we're talking about here. So, I mean, once again, P and Q and all this stuff, like in the scenario where P is true and Q is true, not P and not Q is just a fancy way to write false, right? In the scenario where P is true and Q is true, not P or Q is just a fancy way to write false, right? They're literally equivalent to false. And so because they line up everywhere, they're equivalent everywhere. Does that make sense? Any questions? So this is kind of powerful. So truth tables are very, very, very powerful things, and they're kind of at the base of everything. In a certain sense, the way that we prove, the way to prove this statement, you prove that by doing these truth tables and showing that they lead to the same thing. This being true is shown by this. Which is interesting. This is kind of the base of everything. Like in a certain sense, the definition of what and means is the operation that follows the truth table for P and Q. But anyway.
I have a quick question.
Sure.
Once we establish these as like identities that we know, are we gonna have to go back and show that these exist in the class? Or once we establish that these are actual identities, we won't have to do that?
Excellent question. Once we establish the actual identities, we don't have to go back and show that. So unless, of course, if I were to ask this exact question in homework, it's like a freebie, but I want you to show it again. You know what I mean? But you have all the, like, you could just literally go back and watch the lecture and see what I did. But if you're trying to use it as part of a larger argument, no reason to use it again. Just say, we know it's true. So, because we've shown it to be true. So yeah, if we had to go back and show things in math again every single time we did it, every paper would be 1 million pages long, but really easy to read. Because it would just be a bunch of truth tables with arrows pointing between them. But anyway, it's 3:30, so I will stop there. That is our truth tables. We will do more truth tables tomorrow, and then talk about more of these cool ideas, or not tomorrow, Thursday, and talk about more of these cool identities. Oh yeah. Benyay asked what percent are CS majors. I think it's like 80% of you. It's very high. But anyway, anybody have any questions for me? Okay, well, then have a good day, everybody. Have a good, like second day of class over, right? So there's only like 80 more or something like that. You got this. How's online classes going for people? I mean, we did it last semester, so I guess it's not that big a deal anymore, huh? Some teachers have a problem with Zoom. Is that passive aggressive? Is it me? Some teachers are having Zoom problems. But yeah, I hope it's going good. I know, is anyone in a hybrid math class? Or a hybrid anything class? Thanks, Benyay. Thanks, Benyay. Hybrid physical electronics here. So what's that like? How's the hybrid going?
They have, can you hear me?
Yeah.
Yeah, they've split the class into 2 groups of students. And so one group of students